Okay, so continuity and behavior and symmetry. I'm just realizing that I start almost all my videos with like, okay, so I'm sorry about that. So these are the kittens that are at my house for all you cat lovers. Otto is the orange one, and Athena is the cute little baby. She was born in like April of this year, so she's still pretty young. She's really cute. So cute. Anyways, so continuity. So a continuous function is a function without any breaks in it. And to really like drive this home, I guess, if you can draw a function without lifting your pencil up, it's continuous. So like this right here, say we have this function that goes like this. I can draw that without lifting my pencil. But then if I have a function that looks like this, I have to lift my pencil to draw that. So this one would be discontinuous, where this one, sorry, my handwriting really sucks sometimes on here. This one would be continuous. Okay. So examples of ones that are not continuous. You need to write these ones down. So if you are just going along and there is a hole in there, see how it zoomed in and there's just a hole? A lot of times on the graphs, it will look like this. So say we had like just a parabola, but then it would be like a hole. That's how it will look on yours. This is a hole, making it not continuous. This one, see where we were going, and then it looks like we just kind of jumped down there. That's called a jump. Other ways you might see this is if you have like a function that looks like this, and we jumped up here and went like this. This is like our piecewise functions. We'll get into graphing these at some point. And then asymptotes is the other one. So, and we've kind of talked about this, but asymptotes are, they go along continuously. They're infinite. This keeps going forever, but there's no points. I guess I could do this in another color. There's no points on this line right here. Okay. Okay, so we want to determine if these are continuous, and if not, identify the type and location of the discontinuity. So this first one, it is discontinuous. We could not draw that without like keeping our pencil on the ground. And this is a jump at x equals -5. We always do it with our x values, and it's a jump because we went down from one to the other. Okay. This one is discontinuous, and it has two different ones. The first one is we have an asymptote at x equals 2, but we also have a hole at x equals 4. And this last one is continuous. Okay. End behavior. So end behavior is the behavior at the ends of the graph. We do not care about what's happening in the middle of this graph, okay? You could literally put like a picture of a smiley face right there. We don't care what's happening there. We only care what's happening over here. Okay, we only care what's happening at the very ends of the graph. There. So as x gets smaller and smaller, for this graph in particular, y gets bigger and bigger, right? So we would write that as x approaches negative infinity. So that's the as x gets smaller and smaller, y approaches positive infinity. So y gets bigger and bigger. This is how we write it. F of x approaches infinity. F of x is like the function notation of y. Don't write y though. I want you to write f of x. So as x goes to negative infinity, f of x goes to positive infinity. And yes, you have to write it this way. Okay? So if we look at this one, the other end of the graph, this is saying as x gets bigger and bigger because we're going towards positive infinity for this side, y gets smaller and smaller. So this is saying as x goes to infinity, f of x goes to negative infinity. Okay? You can do it. Let's look at the end behaviors of these graphs. So for this one, that side is saying as x goes to negative infinity, so as x is getting smaller and smaller, f of x is going to 0. It's not going up and down. It is going towards 0. And then as x goes to infinity, so as x gets bigger and bigger, that side is also just going towards 0. Okay, this one, we do not care about the middle. Remember, we only care about the ends. So here, as x is going to negative infinity, f of x is going towards negative 2. And for this side, as x is going to infinity, f of x is going towards negative 2 also. This one, so as x is going to negative infinity, f of x is going up, and that's just going to continue to go up forever, so it's going towards infinity. This side, as x is going towards infinity, f of x is going towards negative 5. Cool? Okay, symmetry. So there's two different types of symmetry that we're going to talk about. There's lines of symmetry. Which lines of symmetry, these are where like you could fold along that line and the two halves would match. So you might remember doing something like this in elementary school where you would take like a square and you would fold it and see how many times you could fold it on top of itself. And you would end up getting, there's 4 lines of symmetry there. Same with like a rectangle, you could fold it twice. Rhombus, you could fold it twice. A kite, you could only fold it once. Isosceles trapezoid, you could only fold it once, but in a normal trapezoid, they would have no lines of symmetry, and so on. Okay, point symmetry is where you're taking a point and you're rotating along that point. So the graph remains unchanged when you rotate 180 degrees. So like this star one, if we rotated at 180 degrees, it would look the exact same. Okay. So x and y axis are common lines of symmetry that we're going to be talking about, and the origin is a common point of symmetry for the graphs. So here, we want to figure out what the lines of symmetry are, and then we're going to try and figure it out algebraically also. So this one, we have a line of symmetry right down the y-axis. So this is going to be symmetric with the y-axis. Now, algebraically, if it is symmetric with the y-axis, write this down. Symmetric with the y-axis means that we are going to replace x with negative x, and it should result in the same equation. So let's check it. So if we have y equals, we're going to replace x with negative x. So this is going to be negative x to the 4th minus 4 times negative x squared. Well, negative x to the 4th, that's the same thing as negative x 4 times. So negative times negative is a positive, times a negative is a negative, times a negative is a positive, so I'm left with x to the 4th there. Same thing here, that's going to be negative x times negative x, which is x squared, so this is just minus 4x squared, which that is the same thing that I started with, so yep, we checked it algebraically, it works. And I think, I just did out the same exact thing here. Always the same. So y-axis, you replace x with negative x. Okay, let's look at this one. So this one right here looks like we couldn't fold it over the y-axis. We couldn't fold it over the x-axis, but could we rotate it? So if we rotate it 180 degrees, it is symmetric, so that means it's symmetric with the origin. So if I was to give you a paper like with this, you could always just like flip your paper upside down and see if it looks the exact same. This is symmetric with the origin, and to check when it's symmetric with the origin, we place x with negative x and y with negative y, and it should result in the same equation. So that's going to be negative x times negative y equals 6. Well, negative times negative is a positive, so that's xy equals 6. Holy crap, I'm Batman. Okay, this one. So this one is symmetric with the x-axis, and that means we are going to replace y with negative y. Please write down all these algebraic stuff. X-axis, you replace the y's. Y-axis, you replace the x's. Origin, you replace both of them. So then here, if I just replace that y with negative y, you can see pretty quickly that it turns out to be the same thing. Okay. Yep. Okay, this one. So this one is symmetric with the x-axis. It's also symmetric with the y-axis. And it's also symmetric with the origin. So it's all three. So that means we need to check all three. So remember, x-axis replace y with negative y. Y-axis replace x with negative x. And origin replace x with negative x and y with negative y. That's a very good table to write down in your notes. So y-axis, negative y squared minus x squared equals 1, which you do get y squared minus x squared equals 1. Y-axis, same thing, you end up getting it. And origin, same thing. And yes, you have to check all three. Okay? Yep. Okay, last thing we're going to talk about is even and odd functions. So this is just, even function is just a fancy way of saying it's symmetric with the y-axis. Odd function is a fancy way of saying it's symmetric with the origin. Okay? So to check algebraically, if you plug in negative x, for the even function, you get out the same function. If you plug in negative x for the odd function, you get the exact opposite. So even is the same, odd is opposite. Okay, that's a good thing to remember. Even, so you always plug in negative x. Plug in negative x. Even is the same. Odd is the opposite. Okay. So let's look at some of these. Let's try and figure out whether it's even or odd. So if I plug in negative x here, I get negative x cubed plus x, because negative x cubed is negative x cubed. And then negative times a negative x is a positive x. So look, these signs have completely flipped. So this became a negative. This one became a positive, which means if they completely flip, that's odd. Okay? Which means it's symmetric with the origin. This one, so negative x squared plus 6, I'm going to plug in negative x. I get the same exact thing, which means it's even. She doesn't even go here. Symmetric with the y-axis. And then this one, I'm going to plug in negative x, and I get negative x cubed minus x squared plus 2x, which some of those signs switched, but the middle one didn't, so that means it's neither. Okay, it can, not all functions are symmetric, so that means that it's just not symmetric with anything. Okay? And that is it. Goodbye. Thank you.